So I'm going to continue where we left off with the blackjack program that we were writing. Okay? And the idea here is that we should maybe make some strategies and see how they play against each other, because we have the dealer and the player. And so we're going to be working on some simplified casino rules, essentially, for the way this is going to be played. And the way this works in the casino, essentially, is, and I'm vastly oversimplifying here, is that the dealer will essentially, if they don't have 17, is that they will hit until they, or in other words, they'll draw cards from the deck until they get to more than, until they get to greater than 17. Okay, once they hit above 17, once they hit 17 or above, they stop drawing cards. Okay, that's the strategy for the dealer. That's the way they have to play. Okay, so we can program that in, and then we can program in a strategy for the player who will lose if he ties, right? Because he has to win. Okay, so we can see, and then we can use that. So let's go ahead and program this strategy in. Now, to call this an AI is kind of an overstatement. This is what you would more see when you play a game and you can choose, 2-player or versus CPU, right? This is very, very basic, which is basically the player. So the dealer will play. So we'll make a method, public void dealer play, which is what they'll do. The dealer will do, and the dealer will do this regardless of what the player's score is, right? We're making this really stupid AI. It's not looking at what the player has, right? Okay, the dealer's just simply gonna draw until they hit 17. This is their strategy. Okay, if they beat 17, they stop, or if they hit 17, if their value of the cards is at 17, they'll stop. Right? The goal of blackjack is to get as close as you want to 21 without going over. Okay, so until okay. So first thing we need to do is get the hand value. Okay, is so we're gonna. This is actually fairly straightforward, right? While this player's get hand value is less than 17, draw deck dot draw. Let's see, this dot hand dot add. Right, so we've got a lot of dots over here, but we're saying we're going to add to this player's hand a card that we're going to draw from this deck. Okay, we're not going to worry about having to reshuffle the deck, because we're just going to be very simple, and every time we want to play a new game, we're just going to reshuffle the entire deck. So we don't really have to worry about worry about that too much. So while this hand's value is less than 17, and we'll have to come back and fix this, because otherwise we might hit into an infinite loop based on the way I want to reprogram the get hand value. Draw. This dot hand up, add draw. So it's just going to keep drawing until we get to 17 or over. Okay. Now the issue is that basically that hands over 20. If your hand is over 21, right? If your hand's over 21, if you bust, in other words, as it's called in the game, then we should probably treat that as a 0. So while this hand is less than 17. And let's say this dot get hand value is not equal to 0. So now this means we have to make a couple changes over here to get hand value method, which would count up these values, right? Okay, so it's going to count up the values. First off, let's add an if statement over here at the bottom. If value is greater than 21, right? If the value of the hand is greater than 21, what we'll do is that we'll return 0 instead, right? If their hand score is too big, we'll return 21. The other thing we want to do is that aces, we've been counting aces as 11, but aces have 2 values, in fact. Aces can be either a 0, or aces can be either a 11 or a 1, right? So we need a way to basically treat we need to find a way to treat our if you have an ace, to be able to treat it as a 1 instead of 11 if you accidentally went over. So while value of the hand is greater than 21, and let's see, and let's say, what do we have here? We have card is equal to ace. So how many aces do we have? So let's go ahead and keep account of how many aces we have. Int num aces is equal to 0. This seems like the easiest way to solve this, because otherwise looking to see if something contains an ace, that's just going to be true all the time. If num aces is equal to 0, we'll do num aces plus equals 1 as well, right? So if we see an ace, we increase our value by 11, increase the number of aces we've seen to 1. Why I'm doing this will make sense in a bit. So while we have our score is greater than 21 and num aces is is greater than 0, what we'll do is that we will go and say num aces minus minus. We'll treat our ace as not an ace. We'll treat it as a 1 instead, right? If that makes any sense. And we'll reduce the score, and we'll reduce our score by 10 points, right? This will keep a player from busting if they get something, if they do something like they draw an 8, they draw a 7, and then they have an ace. Sorry, well, let's say they have an ace and a 2, right? And then they draw a king. So an ace, a 2, and a king. That would normally be 11, 12, 13, plus 10 would be a 23. But with an ace, that allows them to go, that allows them to basically turn that into a 1. Make sense to everybody? So there were a lot of little modifications we made here. So so we counted the number of aces. If the number of aces is greater than, we're gonna basically count the number of aces we see, and while our value is greater than 21, right? If for some reason we would bust because our ace brings our score too high, we'll turn our ace into a 1 instead by subtracting 10 points. And we'll do that if we have if we did something weird, like we drew, we had a 2, a 3, and then an ace, and then another ace, right? Or something weird like that. So we a lot of this code we did already from Tuesday. Okay. So we have the value. So we have an accurate way of getting our hand size now. If you bust for some reason, then your score is going to be so if we bust now, our score is going to be represented as 0. So that's going to be an easy way to do this. So now we can do that. So now we can write a strategy for the player, right? Void. Let's go with human play, and we're going to just set up our own strategy, right? What can we do with our strategy? Right now, all the information, by the way, is completely, it's completely silent, right? But what we do know is that typically you're allowed to do other things, like you can see what one of the player's cards is. One of the cards is typically face up or something, but that's generally used as an aspect of betting and that kind of stuff. So right now we're going into this blind. So essentially what our algorithm is how do we want to adjust this algorithm, right? While we still do we want to play with a different score? Like, do we want to basically say, so I hear that while we've got 16, that's a fairly good strategy. In fact, there's a pretty big table that's an algorithm you can follow. For right now, we'll go and say, if the humans player finds that he's less than 16, we'll draw a card, okay? So now let's go ahead and run that over here in the runner. So here, the human will draw, their dealer will play their hand, then the player will draw their hand. Okay, and then we'll do dealer.dealerPlay the deck, and then player.humanPlay the deck, right? And then we'll run this. And we can start seeing like, okay, the dealer wins that one. The dealer won that one because he had a 7, and then he drew a 3, and then stayed on 20 because that's his strategy. The dealer actually, and the dealer won. Sorry, actually, the human followed his strategy, but he only tied the dealer, which was a bit of a issue. So now how do we can't just now the players won a bunch of one game so far. The dealers won 2. We can't say really statistically who is better unless we run this a whole bunch of times. Right? But fortunately, we have loops for that, right? So why don't we see what what strategy is, and then we can adapt strategies to see if we can't beat the dealer, or at least see, because we lose on ties, how often we're going to lose. So new deck, player. So we've got. So why don't we go ahead? Instead of what we'll do in this one is that rather than we will put this in a for loop. Okay, I'm going to comment out. So first off, I'm going to comment out a lot of our print line statements, because when we're running this a bunch of times, the print statements are actually what's going to be slowing us down. So comment out your print line statements first. The next thing we're going to do is that we're going to create a for loop. Okay, so set up the structure of the for loop and surround your code the code. Okay, then indent your code. My IDE is smart enough to do that. So int I is equal to 0. Then how many times do we want to run this? Let's say we want to run this. Let's say I is equal to, let's say I is less than 1,000 times. We'll run 1,000 simulations of this, okay? I plus plus. Make sense? So now over here, we'll basically go int. Let's go ahead and actually make a final int num games, right? We'll do num games is equal to 1,000, and I'll replace, and that will be the variable we can change over here. That way we don't have to remember we're playing out of 1,000 games. Okay. Int number wins. So this will be the number of times the player wins versus the dealer. Okay. Obviously, when we begin, he starts at 0, and if the player beats the dealer, number wins plus plus, right? And that's it, essentially. So we're going to just count the number of times the player wins. Now, as we go through this, we can see, we can go through this and then sout the player won, let's see. And then we need to deal with percentages, so that would be, let's see. Well, let's first create a fraction, so we need to do 1.0 to make sure that the entire operation becomes a double. 1.0 times number of wins divided by num games. So there, and the reason I have the num games rather than 1,000 is that now if I want to change the number of games I run, I only have to do it in one place. And actually, since it's percentages, we'll make this 100, right? Because this will be a number of wins times number of games will be a fraction. So we'll now add this to a percent sign. So now we run this, and we see that it dealt 1,000 games, and the player won 42.6% of the games. Let's go ahead and see if our answer is different. Oh, this time the player only won 39% of the games. So that's a fairly 43%, 43.1%, 41%. So that's a fairly broad range. So I feel like that if we want to get a more accurate answer as to how often this is going to run, because this is so heavily luck-based, we need to do a few more. Let's try 1,000 more. So 1,000 times more. Let's go ahead and also, where am I revealing my cards? Oh, right, in cards in the deck. So that will basically silence this and should make it also run faster. So now the player won 41% of the game. So now we're becoming more consistent. Now we're running 1,000, we're running 100 times more. We're running 100,000 games rather than 1,000. Running 100 times more of the games. We're getting a lot more accurate with the amount of games. Sorry, with the so the player strategy wins 41% of the time. All right, which, you know, again, because ties count for the victor, sorry, for the dealer here. So that really does put a crimp in our style. If we adopt the same strategy as our whatchamacallit, as the dealer, we actually lose less. So we actually lose slightly more games. Okay. So maybe if we adopt, what happens if we drop down to 15 rather than going up? Right? And this is just a basic way of just kind of evaluating it. Oh, I'm winning slightly more because I'm busting less. And I'm letting the dealer bust more. So I'm winning maybe just a tape, but it's basically 42% rather than 40%. So 42 versus 41. So it doesn't win too much more. But this is actually an interesting way of gathering statistics when you don't really know the answer, which is that basically you can simulate something and run it many times and say, okay, I'm getting consistent answers each time I run this, so this must be how it's done, right? I'm basically running the statistic, I'm creating a statistical sample, and I'm drawing it a bunch of times, and I'm going through it a bunch of times, and I'm pretty certain that this is correct, rather than trying to figure out all the hard math to figure out how often my strategy is going to work. I'm just going to actually perform my strategy a bunch of times. And that's actually kind of advanced technique for doing some problem solving and programming. All right, so now with that being done, so you guys got the next couple of class assignments, right? Which I wanted to give you the chance to work on today. Then we're gonna so essentially this is the last make work assignment. The next assignment will be the game of life, and the assignment about after that will be our inheritance assignment, which will be fox versus rabbit. Okay. Which will be very similar to this in the sense that basically you will be designing a strategy to beat a CPU opponent. Okay. The program works. You just have to find a strategy that improves. The game of life, though, after that isn't so much. It's a 0-player game, meaning there is no, like Minecraft, there really isn't a point to it. There's just, you just play it, and it's a rather simple game. But for right now, I do want to go over our practice exam. So let me start up a new stream for that.